Hello everyone and welcome back to a new video in Robot Structure Analysis Professional 2024. In this video we are going to be talking about support definition and all those crazy types of supports. And I know a new video has been long overdue, but we're back. So this is going to be kind of a short video where we will dive through all the support definitions. And with that being said, sit back, relax and enjoy the show. Okay, so I want to explain all kinds of supports we have, and to do that I'm going to define a very simplistic beam. The reason why I'm defining a very simplistic beam is because it makes it much more sensible for you to see the effect of different support definitions on the beam. So I'll just define me a simple beam of 5 meter length, and of course if you're new to Autodesk Robot, I'll be linking a playlist on the top right where you can brush up on all those principles of robot. Anyway, I defined a beam of 0 to 5 meters, so I'm gonna draw it. It doesn't matter what the beam exactly is, but I just want to show you the different support definitions with that beam. So that's basically a steel beam, W16 by 40, 5 meters of length. And you can of course see the section like this. Let's do some support definitions, shall we? So here I'm going to add me a support. I'm going to add me a fixed support here. And I'm going to add me a pin support here. And I'll delete this test support. I will make me another one very soon. So I have a pin and a fixed support. And now I'm going to define me some loads. I'm going to define me a load type here. I'm going to select dead load. Of course, as you know, dead load comes predefined with its own weight. Now for practical reasons, because I wanted to follow along the support definitions, I'm going to delete the self weight. So I'm going to go to loads, load table, and eliminate the self weight by pushing the delete button. So now continuing with this, I will define me a new load. This load is going to be a member load, and it's going to be dead in the center of the member. Let's say it is 0 in the X, 5 up in the Z. And I'll just add the load here and add a load in the middle. So now we have a load dead in the center with 5 kilonewton force. Now, of course, if I analyze that thing, I'm not supposed to be surprised when I see the deflection shape. Of course, it's a fixed support. So I'm predicting a deflection shape to be 0 and up and a slope here. And if I click on the deflection, you can see exactly that. This is not supposed to be surprising to any of us. So now what I will be doing is I will start playing with the definition of that node. So I click on node support definition. Now, of course, I only have nodal. I could have linear and surface. I'm going to explain it with nodal, but whatever I explain in nodal can be easily extrapolated for linear and surface. So I'll add me a new load. I'll call it test support here, because we're going to test a lot of things here, so test support. And I'm going to release all the directions. I'll add that thing and close. Of course, now I can add it here, so I can select this node, and I can apply it. And despite the fact that it's fully free, you still see a support because it's a trick Robot uses when you apply a 2D system. Meaning, if you go to geometry and open a structure type here, we use the 2D structure. In reality, Robot is not using a 2D structure. It's actually using a 3D structure and behind the scenes playing with all those definitions without you even realizing. So that's the reason why I see this strange thing. Okay, now, if you of course run, this is an equivalent of having a free support because nothing is being held here. And of course, you can see the deflection going up at 1.51 millimeters because my deflection is in meters, so 1.51 is in millimeters. I can check if the deflection is indeed in this unit by going to Tools, Job Preferences, checking the units, and in the others, I can see displacement in meters. Perfect, fantastic. Now, of course, the scale might be a little bit wacky, so I can go to Results and go to Diagrams to Members, Deformation, and normalize that thing just to make it kind of make sense. Fantastic. So far, so good. Now, this deflection, 1.51, would be also obtained if I don't have any support, because that's basically a dead support. Meaning, if I even delete the support here and remove it entirely and run 1.51, keep an eye on that number. If I run that thing again, I get 1.51, no surprise at all. So this support is basically dead, it doesn't do anything. Of course, if you want to change that, you can change that via its support definition. So far, so good. So that's a test support. Of course, if you want to hold UZ and then click Add, this will modify the support by letting it hold UZ, which prompts you to run the analysis again. And if you run the analysis again, you're getting back to the pin thing, where you have 1.35 and mid-center displacement. Now let's start our investigation. I will remove the fixed direction UZ, and now once again it's free. So if I calculate now, you shouldn't be surprised if you see 1.51 again, which is perfectly sensible. Now what about uplift? That's the first topic of today. Well, uplift basically allows the support to resist in one direction only. Meaning, if you say uplift use it positive and hit the add button and change this, let me show you what happens here. So if I run the analysis now, you get no reactions at all, because use it positive means that this only supports a reaction that goes upwards. So if the reaction is upwards, you will see it. If the reaction is downwards, it will be set to 0. This can be well used for modeling soil, but I will leave this for another support, which is elastic. Elastic is more valuable to model soil. But okay, uplift, you can use it if you know that the material is resting on a plate, for example, or soil where you only can resist compression and no tension. Now what happens if I flip this direction of the force, because that's 5? Well, if I go to loads, load table, and flick the direction to become -5, and push the enter button, of course now it's changed, so I need to calculate again. You can see the force going down. And if I calculate again, then lo and behold, suddenly I have 1.35 down, and you can see this thing is resisting now. You might be wondering what the reaction is. Well, to see the reactions, you go to results, diagrams for members, reactions. I will activate everything and show everything. You know what? Let's activate FZ for now, because we are focusing on FZ. You can see the reaction is reaction, basically. Now, if we go back to loads, load table, and flip the direction of the load to the opposite, you will see that the reaction no longer is supporting, it's no longer active, because I told you we used uplift, use it positive, meaning that the reaction will be available if it's up, but if the reaction is supposed to be down, it will be 0. You can see here that the reaction is supposed to be down because the force is going up, nothing happens here. Now UZ minus is the exact opposite of that thing, meaning that if the reaction is going down, it will exist, and if the reaction is supposed to go up, it will not exist. Like if I run the analysis here, now suddenly the reaction exists because it's going down. But if the reaction was going up, oh wait, that's a nonlinear reaction. I think I messed up. Give me a sec. Yeah, it's a nonlinear reaction. Let's just remove that thing. Okay. That's a nonlinear action. Let's just run again. I think I messed something up. Yeah, exactly. Now everything is fine. Everything is perfect. Let's go back and check with, where is it? There we go. Yeah, uplift, UZ negative. Let's just reiterate the entire thing, because I think my software has just glitched. And UZ negative, you can see that nothing is supposed to happen because, oh wait, no, sorry, everything is supposed to happen. Because the force is going up, and the reaction is supposed to go down, so it exists. Of course, if I flip the direction of the force, I will not see any reaction, because if I make a force going down, the reaction is supposed to be up, but you have UZ negative here, so it doesn't exist in that case. Anyway, this is what uplift means. I usually use UZ positive if I want to model soil. For now, that's what I wanted to talk about in rigid, so I'll click on add now again. So now we are back to square one. We have our support removed, and we are back at 1.51. Let's go to elastic now. Now elastic is basically adding a spring here that resists. So let's do this. I'll click UZ here, okay? Now, I will add me a spring at UZ. By the way, if you click UZ like this, you are fixing it. And if you remove the click, you are freeing it. If you want something intermediate between fix and free, you can add yourself here a support spring. For example, I could put here a 100 as an example. If I add this now, it changes the support. Remember, this is still a test support. You can see the spring shape here. If I run the analysis, let's see what happens. I get a reaction, of course. That's not an uplift spring, by the way. It's a totally fine spring. And you can see the reaction is negative 1.377. But why? Well, it's very simple, actually. The reaction here is going to be the multiplication of the displacement at that point by the spring coefficient. So displacement is 1.38 going up. And if I multiply 1.38, no, it's actually 0.00138 because of the exponent. If I multiply this by 100, I get 0.138, which is almost what you see here. So it's just that the reaction is going to be the displacement multiplied by the spring, which is easy, I guess. I usually use this if I want to model rafts. I have a perfectly functioning raft video that I will link on the top right. So take a look at that if you want to see how planar springs work. I actually dissected that thing in detail. Anyway, this is elastic. Let's go to friction. Friction is interesting. Now, before I go to friction, let me put this back to 0 and basically reset the entire thing just to make sure we are back to our 1.51 displacement here. And we are back. Perfect. Now I go to friction. What is this friction thing? Well, friction is not only friction. That's a lie. In reality, if you click on the button friction, now I have to tick it. If you click on the button friction, you can see that friction has 3 components. It has a friction coefficient mu, and if you remember from physics and soil mechanics, both actually, if you have a surface, then this surface has friction, and it has cohesion in soil mechanics here. Of course, the friction will result to a reaction. How do you get the reaction? Well, if you have a normal force, then the friction reaction, pardon my errors, is going to be mu, which is the friction coefficient, multiplied by n. Now, this mu has equations in soil mechanics, like tan lambda, or tan alpha and stuff, and angle of repose, and angle of etc. Now here, basically, it tells you what the friction coefficient is, which is basically the multiplier that you multiply with the normal force. The cohesion here is in kilonewtons. Basically, the cohesion is the amount of cohesion that is provided by the surface. And I know that in soil you learned about cohesion to be in kilonewton meter square, but since we are talking about a line, you can easily convert the kilonewton meter square to kilonewton by multiplying by the area basically. This can be used in detail if you change this to area support. You can use this to do some checks on retaining walls if you want. But in reality, you don't really need to do this because Robot has a perfectly functioning retaining wall check in the sliding and rotation domain. What about GM here? Believe it or not, I mean, I clicked on the help, you can click on it. GM, it's a very strange word, but it means safety coefficient. So if you say 1, it means no safety coefficient. We'll just take it as it is. I don't know why they called it GM, to be honest. It could be a different thing, but they just use it GM for the safety. I'll keep it as 0.4 and just click OK. So now you have the friction here. And you can have friction on 2 sides. You can use friction this or friction that. Now, what is this and that? Of course, in 3D, you have the 3 directions. This is the direction of the bearing pressure force. If you click on UZ, this means that you have this typical scenario where the force is in Z and the friction is, of course, perpendicular, which means in the X. Now, you could have a different scenario where you have a wall and the bearing pressure is coming from the X, which means that the friction is going to be in the Z direction. Now, for that example, I'm going to assume the bearing pressure force to be in the X. So I'm going to assume I have this. So now I have to find my friction support. So what shall I do now? Well, I'm going to apply it, right? So I click add and say yes, of course. And of course, my UZ is not fixed because it's frictioning. Now, if I run, you think everything is fine. But if you know my channel far enough, you know that if I say everything is fine, then nothing will be fine. Because if I run the analysis, 1.51 will remain 1.51. So let me show you. And there we go. It's still 1.51 despite the fact that we defined a friction. Of course, the question is what gives? What happened here? Well, I will tell you what happened. Physics happened. You see, the friction force is going to be the multiplication of the normal force multiplied by the friction angle or friction coefficient. If the normal force is 0, the friction force is 0. Now, did this case happen in my case? Well, yes, because the normal force in my case was 0. The friction is 0. Let me show you. There is no force in the X direction to give you a normal force. Now we need to, well, that's why you get a 0 reaction here and nothing changed. Well, I can show you how it works if I, for example, add me a force. So if I go to node here and click on node force, let me add 1 kilonewton just to show you on this node. So I'm applying a 1 kilonewton force. So now I have a 1 kilonewton force, and by the rules of physics, the 1 kilonewton force bearing on a wall is supposed to give me a 0.4 kilonewton friction force. Why 0.4? Because the friction coefficient is 0.4. If I run the analysis now, well, that's exactly what I will get. You can see that suddenly I have a FZ of negative 0.4. Because the friction is at 1, the bar has a tendency to go up, and because the bar has a tendency to go up, the friction is going to resist the tendency of going up. You would ask, of course, the question, wait a minute, is this static or kinematic friction? That's a good question, and Robot doesn't care, to be honest. Like for it, the friction is basically force multiplied by normal force by friction coefficient. There is no distinguishing between a static friction and a kinematic friction. So it's just a friction coefficient. I hope this makes sense. I'll remove the friction here and I'll add this again. So now I'm basically eliminating everything. If I run the analysis again, I should get my trusty 1.51 millimeters, which is exactly what I get because just eliminated the friction. And of course, this force is a relic of the past. I should delete that thing. So I'll go to loads, load table, and delete this cute force. So, well, let's delete it once the computer replies. Okay, so the force has been deleted. Let's run it again. Nothing will change because the X force has no bearing on the Z direction. Of course, you would think, wait a minute, if there is an X force, it's supposed to have some degree of effect on the Z deflection. No, because linear analysis. If you're in the nonlinear P delta analysis, then it will have an effect. Anyway, let's go to gap. And for the better of me, I never was able to make the gap work for some reason. Like if I, for example, now first of all, let me show you something. If I put here 0.002, why did I choose this value? Because I know the friction, because I know the deflection is 1.51, so 0.002 will not activate the gap, then nothing will happen. Now what is a gap? Well, from the name, it's basically a gap, meaning if I have an element like a beam like this, and it's fixed on one side, and it's being pushed by a force up, if I add me a gap, let's say the gap here exists, there's a gap. Gap means that the reaction will only activate once the beam touches that gap. As long as the beam doesn't touch the gap, nothing will happen. This is one of the hard contact problems, by the way, because there are two conditions. Condition one, where the reaction is inactive because the force is not touching the gap. And condition two, where the reaction is active because the force is touching the gap. Now please note that this is different from the Newman-Dirichlet boundary conditions for finite element, because if you say finite element boundary condition 0.5, you are forcing the beam to have 0.5 deflection. That's not the case here. It's a boundary condition that gets activated once you reach a certain threshold. And it's not responsible for the entire reaction, of course. Anyway, that's what the gap is. But for some reason, for the better of me, it always diverges in this case. Let me show you. If I click add here, now this gap has been intentionally chosen to be larger than the displacement, so that the gap will not activate, meaning if I basically just run the analysis, then nothing will happen at all, because the gap, of course, there's convergence, but there is nothing here, because the deflection is smaller than the gap didn't activate. Now, if I make this 0.001, then all chaos breaks loose. If I run the analysis now, you can see some zigzaggy stuff with the convergence trying, and it doesn't converge. And for the better of me, I have no idea how to make it converge, to be honest. It tries. I mean, if I look here, you can see 9.97. I think it's almost converging. Like, not sure. Let's see. But no, it's not conversion. Now, one telltale sign of not conversion is the summation of forces. Because look, I mean, the deflection is 9.97. That's okay because it's almost the gap. Yes. But the reactions are all over the place. They're wacky. You have like 3.31 negatives, negative 0.084, and 5 positive. So the summation of reactions is not 0. And for the better of me, I have no idea how to get this to converge. Please tell me in the comment section if you have figured it out. My running theory at the moment is that I'm using such a small gap and so small numbers that numerically it's unstable. But of course, you can always tell me what the case is. The final support for today, because I'm not going to talk about damping. Damping is for dynamics. The final support for today is the definition of nonlinear model, nonlinear support. Now, what's the difference between linear and nonlinear support? Not much, to be honest. Now, I know that for some reason, nonlinear always makes PTSD for some students. Like, oh my God, this is nonlinear. Actually, it's not that complicated. And I'm going to show this to you. So let's make a nonlinear model, right? So if I click on UZ, I want UZ to be held in place with a nonlinear model. Now I made the model already, it's called Testos, but how did I even get this? In your case, you will see a none here. Well, you can go to definition because you cannot select a nonlinear model here. You have to go to definition of nonlinear model and define yourself a nonlinear model. I have Testos here, which I defined already. I will delete it now because I want to define it again. So how do you define a model? You write the model name and click add. You can define a force displacement or moment rotation. Now, because we are dealing with forces here, I'm going to define me a force displacement nonlinear model. I clicked add, so now I have testos. And if you want to modify it, you select it first, and then you go to parameters. In parameters, you can choose any model you want. If you choose linear, then it's defeat the purpose, because you want a nonlinear model and you're going to linear. Like, what even gives? You can just choose linear here, right? Or elastic. What's the point even? You can choose bilinear, which is what I want to choose. You can choose rigid with hardening. You can choose all. Of course, those all are complicated words for a simple thing. It just tells you what the definition is. You can see a graph with the values that define the graph. For example, here, this is almost concrete and perfectly plastic. Oh, that's nice. I'll go for bilinear, which is the simplest of the nonlinear models. Here, I am going to, what is the meaning of bilinear? It means that you have a certain strong resistance up to a certain displacement and then a weaker resistance. If you want perfectly plastic, you turn this to 0, which is not what I want. So now I have a bilinear model, which gives you a K of 100 kN up to 5, and then 20 afterwards because it got weaker. Now, let me show you what happens here. I click OK. So now we have defined the testos model, which I can select now, and I'll save this nonlinear support. So now the support is nonlinear. If I run the analysis, I will get the linear reaction, by the way. You won't believe it. I will show you. So I ran the analysis. I got negative 0.1377. Now this is eerily similar. If you go back in the video, this is exactly the reaction we got when we did a linear support. How did I even get that? Well, if you look here, you can see the displacement being 1.38 millimeters. So 0.00138, because, exponent, multiplied by 100 is 0.138, which is exactly what I got here. Why did I multiply by 100? Because that is the definition of my model. You can see here that if you go to parameters, you can see that the K is 100. But we think, wait, why did the 20 not play any role? Well, it didn't play any role because you haven't passed the second threshold, or the bilinear threshold. The threshold is 5 millimeters, or 5 times e negative 3. We didn't reach that here, obviously. We just reached 1.38. We didn't reach the 5, and that's the reason why the only stiffness we got is this one. Allow me to explain. Due to the fact that our deflection is 0.0013, we actually are here on the deflection, or we are here on the nonlinear spring diagram. So if you want to reach that location, we need to have a bigger displacement. So let's run it again this time. But this time I'm going to change the 5 to 20 to see what happens. So if I go to loads, load table, I'm just going to increase the load so that I can increase the displacement. So if I go to load table and click 20 here, and then close that thing and run the analysis again, then suddenly something happens. I know that something happens because you can see the displacement is 5.55. It's more than the threshold. So, and you can see a reaction of 0.51. Now I need you to focus here, because that's again something that you need to understand. Our deflection was 5.55, e negative 3. Our threshold is 5 e negative 3. So in other words, we are indeed in this domain. We are indeed in the second line domain. So the K seems to be 20, right? So what is the reaction then? You would think, but you are wrong, you would think that reaction is simply 5.55 e minus 3 multiplied by 20. This is obviously wrong. No, that's not the reaction. The reaction is going to be a summation. It's going to be, because you have two springs, right? Like this is the reaction. Like, let me show you. This is your reaction force. This is the one. Now, how do I get this reaction force? It's a summation of two reactions. It's a summation of the first line part, which is this part. And it's a summation of the second line part, which is in orange, this small part. So how do I calculate that then? Well, it's 5e minus 3 multiplied by 100, that's the first part, plus whatever excess I have, which is 0.55 e minus 3 multiplied by 20. Now if I use the calculator here and say 0.005 multiplied by 100 plus 0.055 multiplied by 20, I get a reaction of 0.511. Lo and behold, 5.11. So yeah, I hope that you have gained a good understanding about all the possible support definitions you have in Autodesk Robot. I know I explained this with displacement. You can easily extrapolate this for rotation, linear, and planar support systems. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a non-linear sized shout out to my dear channel members in the contributor level and the helper level. And I want to thank them first of all for their patience because I haven't been active for some time. So I want to thank them from the bottom of my heart, as the support is important to me and enables me to provide you with videos. I don't know if I can, so hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and I earned a subscription from you. If you have enjoyed, please subscribe, like, share, and so on. Especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video. Bye bye.